Hello and welcome to Tribe Topper. In this video session, you are going to learn about polarization. So what is polarization? If you can see the diagram, you will quickly understand. Basically, what we are doing here is we are restricting the orientation of the oscillation of a transverse wave. So basically, polarization is nothing but just a phenomenon of restricting the geometrical orientation of the oscillations for a transverse wave. Like if you look at this, now this was an unpolarized light oscillating in all directions. Now if you pass it through a polarizer, only and only the component which is parallel to these slits, right, the direction will be easily able to pass through it. The ones which are going like this will get restricted. They get an obstacle, so they are not able to pass through it. So if you look at it carefully, your unpolarized light looks like this, but your polarized light looks like this, where you have a single direction in which this is oscillating in a single plane. So we have polarization of a transverse wave, which is happening here. It restricts its oscillation only to a plane perpendicular to the direction of propagation. The direction of propagation is left to right, and the oscillation is happening in top to bottom. So the polarization of the transverse wave has restricted the oscillation to the plane which is perpendicular to the direction of propagation. That means polarization is exhibited only by the transverse waves. This is not applicable to longitudinal waves. So we would say longitudinal waves, which we know are sound waves, they do not exhibit polarization because for them the direction of oscillation is parallel to the direction of propagation. So how can you cut out that component? Right? Because we want to restrict only to the plane perpendicular to the direction of propagation, but we have nothing along the perpendicular direction. So they are, we can say, in a way already polarized. So longitudinal waves cannot be polarized, only the transverse waves can be polarized, where we are restricting the oscillations only to a plane perpendicular to the direction of propagation. So this is how the light looks when you have unpolarized light like this, either vibrating in two planes or in many directions, right? These two represent unpolarized light, but after passing through a polarizer, only the component parallel to this will go out. So this is polarized light. This is how it looks. We have a daily life use of this, that is, we wear the shades, the polaroids, which actually cut out the high intensity of from all directions, and it doesn't give a glare to our eyes. So the most common method of producing the polarized light is to actually use a polarizing filter, which we call as polaroid. So we have sometimes we check it out with two methods, not two methods, but we use two polarizers. So the first polarizer is something which suppresses the unaligned components of that unpolarized light. So there are no unaligned components which will pass through the first polarizer. So that's why the output of the polarized light, which is coming from the first polarizer, its intensity is half of the incident unpolarized intensity. So we have to remember the intensity coming out of the first polarizer is always half of the unpolarized light intensity. And the second polarizer, which we also call as the analyzer, that also absorbs some energy. It further reduces the intensity of the output, but this analyzer reduces the intensity of the output based on the angle between the polarizer and the analyzer. Like you can see here, this is my analyzer and this is my polarizer, and this is the angle between them. So the intensity of the output coming from the analyzer or the second polarizer depends on this angle, and this is determined by the Malus's law. And the Malus's law says that the intensity of the light coming out from the analyzer, is equal to I naught cos square theta. Now, since I'm saying it depends on the angle between them, between the analyzer and polarizer, therefore that means if theta is 0, theta 0 means that analyzer and polarizer, they are having their transmission axis parallel to each other. So when they are placed parallel, theta is 0, cos 0 is 1, which is a maximum value. Therefore, the intensity coming out would be equal to I naught. So that means if your analyzer is placed parallel to the polarizer, to the first polarizer, you will get the same intensity coming out, which is incident on it, right? So output is same as that of the input. That's in the case of the second polarizer, I'm saying. For the first polarizer, when the unpolarized light enters, it has to reduce the intensity to half. So here we have a question which will clarify how to use Malus's law. So unpolarized light of intensity I naught is incident on a polarizer. The transmitted light is then incident on an analyzer. So the axis of the analyzer makes an angle of 60 degrees to the axis of the polarizer. So you have theta to be 60 here. Calculate the intensity which will be emitted by the analyzer. Now we know that first of all, the unpolarized light of intensity I naught, when it falls on the first polarizer, the intensity I1 that will come out of the first polarizer will be I naught by 2. Now this I naught by 2 intensity when falls on the analyzer, then it depends on the angle. So I double dash is going to be I single dash times cos square 60 because this is incident there. So I'll replace it as I naught by 2 is incident on the second one. Cos square 60. Cos 60 is half. So cos square 60 is 1 by 4. Therefore the I2 that is coming out of the analyzer is 1/8 of I naught, which we would say is 0.125 times I naught. So this is how you can figure out the intensity of light that is emitted by the analyzer. So that's all in this video session. You are going to learn about reflection and refraction in our next video session. Thank you.